So let me start with this last final part of the noise analysis series video. Okay. So I'm considering this as a separate topic, even though we have already discussed about it. Now, when I say about representation of a noise, any given circuit, how did we evaluate those noise is basically by looking at the output port. Okay. We call such kind of noise that has been analyzed at the output port as output referred noise. Okay. So this is one of the type of representation that we have, which is referred as output referred noise. And there is also one more kind of representation, which is obviously the input referred noise. First, let me discuss about this output referred noise, and later we'll discuss about this input referred noise, how to compute this input referred noise directly from the output referred noise. Clear? Now, this output referred noise in general is the way by which we actually compute the noise in a lab or in a simulation. Okay? So whatever we compute in reality, it is the output referred noise. But the other way around, the input referred noise cannot be measured from the input side. Okay? But this helps us in a completely different way. I'll talk about it, but the way that we measure the noise in a lab or in a simulation is by looking at the output port. Okay? And we call such kind of noise analysis as the output referred noise. Clear? So I'll just begin with this simple example. Okay. So now that we are talking about the output referred noise, whenever we are not being specified anything, just asking for the total noise voltage. Okay. So whenever we have a term just to calculate the total noise voltage, we are actually referring to output referred noise. In case if we are specific about the input referred noise, we will mention that in the question. But until otherwise it has been specified, by default whatever we are trying to compute is basically the output referred noise. Clear? Yeah. So now for this, what are the noise components that exist in this set of circuit? Yeah, R has some noise. What type of noise this resistance has? Thermal noise, right? And what about the mass transfer? What are the noise components that are there in this? No, not. Does the R naught contributes to noise? The channel actually contributes to some sort of noise. Okay, the conductance of the channel. But it need not to be equivalent to the R naught. Okay, R naught is just a small signal resistance. Clear? Yeah. So we have two type of noise in the MOSFET. One is the thermal noise. The other one is the flicker noise. And the flicker noise video just I uploaded last night. Okay, so you might not be aware of it, but I'll write down the formula of it. Clear? Now each of these noise sources have predictable quantity. Okay, so what is that predictable quantity that we are talking about? Can I predict the variance of it, or can I predict the power spectral density? So what are these two terms? PSD, right? So any noise, we always have a predictable PSD term. Okay, so we know the PSD, and from which I want to evaluate the mean value or the power of it. So how will I do this conversion? How will I translate a power spectral density quantity, which is in frequency domain, into a power or a variance? Yeah, Wiener-Kitchen relation. So Wiener-Kitchen relation tells us to make an integration over this power spectral density over a set of bandwidth. Clear? So first what we do is that let us try to reflect the power spectral densities of each of these components. Okay. Now which type of power spectral density component you want to represent, either as a current component or as a voltage component? Which one would be ideal for the circuit that I have given here? So it is better if you could able to make it in terms of a current component, and then because the current can actually flow and add up together. Again, I have two components here as far as the mass transfer is concerned. So the resistor has only one single component, which is thermal noise, but the MOSFET has two components. One is again the thermal noise. The second one is the flicker noise, or 1 over F noise. Okay. Now a thermal noise of this mass transfer in general is represented in terms of current. Okay. So And the power spectral density of such thermal noise is returned as something like, so what is this power spectral density of this mass transfer current? Yeah, 4 kB T, yeah, gamma into Gm. Am I right? Yeah. So what is the value of gamma when the transistor is in saturation regime? 2/3. If the transistor is biased in a triode region, then this gamma will take a value of 1. Clear? Yeah. Now similarly, I could represent the thermal noise of a resistance in terms of a current component by representing this. I think I have to have some sort of index value in order to distinguish the thermal noise of the resistance from the thermal noise of the mass transfer. So I'll just add one more index to it. Clear? The index could be an R here, and this index could be M. I'll use M for denoting the mass transfer. Okay? Yeah. So what is this power spectral density of a resistor? Yeah, it is 4. Okay. So these are the power spectral densities of these two quantities. But when it comes to flicker noise, the flicker noise by default will have a power spectral density in terms of voltage. The voltage at the gate terminal. Okay, and that gate voltage has to be converted in terms of a current component at the drain. So we need to convert it. Okay, a flicker noise is modeled as a kind of noise voltage component. It's always defined in that way. But what we wanted is, so noise voltage at the gate, but we want to convert this noise voltage into a noise current at the drain. So I need to perform some sort of conversion. So how will I convert a noise that is existing at the gate terminal to a noise as a current component at the drain? Yeah, Gm square, because the transfer function between this input to the output as a current is nothing but it's our Gm term. Clear? Yeah. So first let me write this power spectral density of this noise voltage at the gate. So the power spectral density at the gate terminal is written as something like, there is again one more term K. So in order to distinguish this K from the Boltzmann constant K, I've just denoted Boltzmann constant as Kb and this one as just K divided by Cox into length into width into 1 over F. Okay. So this is the power spectral density of a flicker noise. Okay. So you can just go through the video back. How did I wrote this particular expression and what is the meaning of it? Clear? But as of now, we'll just take only the value of it. Clear? So now this one I need to convert into a power spectral density in terms of current at the drain. So I think there is a theorem from your communication course which states that we need a transfer function that has to be squared into this. Okay. So one could convert the power spectral density of one form to the other form through a transfer function squared. Okay. Now that transfer function that we have between the gate input and the drain output is nothing but the Gm. Okay. And this value of Gm has to be squared with this power spectral density. So now that I have all those power spectral density in terms of current, now since all of these three components are in terms of current, I can just add them up because everything appears in parallel. Okay. Does this make sense? You can just add the current sources, something like this. Okay. So one of the current can be taken as this power spectral density, and there is again one more current power spectral density, and the power spectral density of the noise contributed by the resistor. Okay, so all these three power spectral densities are appearing in terms of parallel combination with respect to the node V out. Clear? So due to which I want to evaluate the total noise current through this output port. So what I can do, I can add those power spectral densities. Clear? So the power spectral density at the output is nothing but the summation of the power spectral density of the resistor plus the power spectral density of the flicker noise plus the power spectral density of our MOSFET. Are you clear? I've just removed the suffix of 1 over F and the thermal. Okay. That is fine. Now that I have this power spectral density of the total current at the output port, but what question was asked is in terms of noise voltage. So how will I convert this current into a voltage? Yeah? Yeah. So we know that I into R will give us the voltage. So R is something that we need to identify for the given circuit. Now what is the value of R that I have across the output node? Yeah, R in parallel with R naught. Okay, so if that is my transfer function. So for the first term, what we have is 4 kBT divided by R, and for the second term, the flicker noise is given by the top expression, and for the third term, it is again 4 kBT gamma times that of GM. Was that is clear? Yeah. So I also specified something in the video. There is a term total. So whenever there is a term total, what we supposed to do? Yeah, we need to apply the Wiener-Kitchen relation to convert this power spectral density quantity into a power term, right? So now I'm not going to do that. Let us leave this as it is. Okay. But in short, one could find the output power as integral running from minus infinity to plus infinity, integrating this power spectral density at the output with respect to the frequency. Okay. Yeah. So now we'll just talk about the drawbacks of this output referred noise. Okay, so now let us consider that we have a CS amplifier with V in, and there is a V out, and we call this V out as V out 1. That is being connected to one more stage with a gain of A2, and this A2 amplifier is a noiseless. And we have already computed what is the noise coming out of this first stage, that is our CS amplifier. So what was that quantity? Yeah, it is nothing but SV of out. Okay, whatever I've written down here, this entire quantity is denoted as a noise at the output of the first stage. Okay, and I'm labeling it as SV of out in terms of noise voltage source, and its power spectral density is given by this term. Now what happens when this signal or the noise signal is being passed on to the noiseless amplifier A2? What happens to this output, which I labeled as V out? What happens to this V out 2? Yeah, noise will get amplified. So now let us write the power spectral density at the output of V out 2. So let me write it as SV out of 2, and let me label this one, the first stage output, as SV out of 1. Yeah. Now what would be the value of this power spectral density? How will I evaluate it? Yeah, so it is just the gain or gain square, because the transfer function between this port to this port is A2, and that has to be squared while we converting the power spectral density. Clear? You could able to see that the noise is coming only from the first stage, but when I look across the output port, I could able to see that this noise is being magnified by the gain of the second stage. And it seems that as a whole, when I consider the entire circuit, you would see that the noise is so large in this particular circuit, right? It seems to be so large just because of this squaring term, even though it is a noiseless, and the actual noise is just V out 1. But for me, when I look from the output port, it seems to be something like V out 2. Okay, are you getting it? Yeah. So people like me would generally consider that okay, this circuit is not good for me just by looking at the output port. But people like you can work with a signal to noise ratio factor. What happens when I pass a signal from the input Vin to the Vout 2? That will also get multiplied by this A1 times that of A2, right? So when you take the ratios, this factor A2 square will be automatically cancelled when you consider the signal to noise ratio. But a person like me will never do that. I'll just see, okay, this class is not good, and then I'll just move on, right? So it is something like that. So I'll just look at the output and see that this amplifier is giving us too much of noise out of this circuit. This is what I would feel. Okay? So this is one of the case why we don't want to refer to an output noise, rather than it is always better to talk in terms of an input noise. Clear? And also, say for example, you have two circuits and you want to compare what is the noise produced by both these circuits. Now in that case, say for example, I have circuit number 1 which has a gain of something like A1, and the circuit of A2 will have some other gain. Now in this case, I will have a different value of noise in the first circuit. Let me write it as SV of A1, and this will have a different power spectral density across this second amplifier. Now that when I compare, does this comparison actually make sense? Are you clear with my question? The question is that I have two circuits and I'm just trying to compare the noise produced by each of these circuits, and I'm saying that each circuit has different gains in them. Clear? In such situation, comparing the output noise, does it make sense or not? That is the question. Yeah, just because it will have a different R components at the output, and totally the noise that is being referred will be dependent on the gain of this particular circuit as well. Okay, so due to which a comparison at the output never makes any sense. So whenever you want to compare two circuits, it is always better to go for input referred noise rather than comparing to the output referred noise. So now, how will I calculate the output referred noise for the circuit that I have drawn here? For this, we know the value of SV out 1, right? I want to calculate what is the power spectral density at the input. What will I do it in order to convert? Divided by gain. Yeah. Just by using the simple relation, I could write this SV in as something like the power spectral density at the output of first stage multiplied by the transfer function of this system, and that transfer function. So just by substituting this onto the expression that we have got in the previous case, I have to divide this entire quantity by a factor of gm1 square rho1 in parallel with r the whole square. Okay, and the result of this is nothing but my SVN. So now that I'm going to do an important problem, and this was widely asked many times in the CIE as well as in SEE. Okay, so please try to concentrate. There will be some small modifications in the circuit, but once you get an idea, you can apply to any type of circuit that is given. Clear? Yeah, so calculate. All the three part has to be calculated. Yeah, so how will we start with the first quantity? You need to first identify the noise sources that exist in the circuit. Okay, so we know that both this transistor has thermal noise in them, and the way that I can represent those thermal noise is by having a current, or in terms of a current component. Okay, so I could add them together by having this in terms of power spectral densities. It is nothing but the power spectral density of this thermal noise due to M2 plus the power spectral density due to M1. Clear? Now what are those quantities? Yeah, it is 4 kBT, and the gamma is going to be same just because I'm going to assume both the transistors are in saturation. So I pull this term out. I have GM2 plus GM1, and that is my output power spectral density in terms of a current. So what is the power spectral density at the input? How will I convert them? So what is the transfer function from the output current to the input voltage? How will you convert? GM, right? So it is 1 upon GM or into GM transfer function. From the output we want to convert an input. 1 by GM. Okay? Yeah. So the transfer function to convert an output current to an input voltage is 1 by GM. Okay? We are moving in the opposite direction. Due to which I have H of F, which is equal to 1 by GM of which transistor? M1 or M2? M1. So I have to put this M1 here. So now that we calculate the power spectral density at the input, okay, so whatever we have got is just the power spectral density, but how will I convert them in terms of variance or in terms of power? So we have to use the Wiener-Kitchen relation in order to convert this power spectral density into a variance term. Okay, but since because nothing is specified in terms of frequency band, the band that I am going to assume here is 1 Hertz. And since the SV in is completely independent of the frequency term, I can pull them out, and when I try to do this integration, I would get F2 minus F1, and this bandwidth I am going to assume it as 1 Hertz. So now that we have done with the first part, let us do the second part. The second part is to calculate the total output thermal noise if the circuit is driven by a capacitive load. Clear? So I have to add a capacitor at this particular node. Okay, and also clearly you could be able to see that there is a total term that is sitting here, right? Now let us try to compute this value. So in order to do the second problem, first we need to compute the power spectral density at the output. Now how will I convert this power spectral density in terms of a voltage if I know the power spectral density in terms of a current? We know this value, right? I know this value. From this value I want to convert in terms of a voltage. What is this transfer function that exists at the output? Yeah? Yeah, I have a resistance. What is the resistance that I have here? When I look through the drain of M2, RO2, when I look through the drain of M1, I have RO1. Okay. So now how will I convert a current into a voltage is by making the current to flow through this impedance structure. Okay. Now what is that impedance value that I would get, which will act as a kind of transfer function? What is the transfer function that I get out of this? Using this transfer function, I need to convert this power spectral density of a current noise into power spectral density in terms of a voltage noise. Okay. So what is this H of F? How will I write this H of F after removing all these parallel symbols, or at least removing this parallel symbol between the resistance and the capacitance? What type of term I will get? Yeah, so the conversion of this is H of F that is equal to, is this correct? Yeah. So now whenever we are talking about a steady state response, obviously the S term will be changed to j omega. So I'll just use that j omega here. And now I'm trying to identify the modulus of this transfer function. Clear? So I have an imaginary term sitting here. There is a real term. So how will I take the transfer function of it, or the modulus of this? 1 divided by square root of real part square plus the imaginary part square, right? And the whole thing has to be squared at the top. Okay. So this is my transfer function in terms of magnitude of it, and that has to be multiplied by this SI of O. R at the top, right? This is right? Okay. So now I want to calculate the total power at the output. So use your Wiener-Kitchen relation in order to compute that, and let me know the answer for it, because it's an integration. So perform this integration and get me the final value. You just think wisely and see which are the terms I can remove out of this integration. Obviously, the first term never depends on any frequency I can pull out. Even this numerator can be pulled out. The only thing that is dependent on the frequency is this particular term. Okay, so okay, rather than writing it as R01 in parallel with R02, I just use a capital R here. Okay, equivalently. Now, what is this integration of this particular term? What value you would get out of this integration? A tan inverse of this quantity, right? And we have to apply those limits of 0 and infinity to the value of x. Okay, yeah. Yeah. So now this tan inverse term would then get converted in terms of pi by 2. But I also have to pull out some common terms, right? There is some other common term will come. It is not the direct integration of this will come. We have to convert. I think it has to be multiplied by some factors, right? So if I consider x to be equal to 2 pi f CR, yeah. So I have to multiply and divide by this 2 pi FCR. Yeah. So now the integral will be proper. Okay. So now that I have a pi by 2 term out of this tan inverse, okay, and when I apply the limit of 0, it is just a 0 term. And here I have one R being cancelled out, and I have this 4 kb T gamma gm1 plus gm2 divided by 2 pi. Again, the pi's could be cancelled, and this 2 and this 2 with 4 could be cancelled out. So finally, I would end up having the total power at the output as and always remember that you need to substitute the value of gamma. Okay, so at the end of the result, ensure that you are using that gamma value. So now that we computed the noise power at the output port, we still have to identify the SNR. Okay, now as I said in the question, you have a signal, okay, a sinusoidal input signal with a magnitude of Vm. So the peak magnitude of this sinusoidal input is Vm. So what is the mean square value of it at the output? I have a sine waveform with a magnitude of Vm, and what is the RMS value of this? Huh? Yeah, correct. Okay, sorry. So RMS, yeah, so this is the RMS value. And this RMS value, when you pass it through an amplifier, which is nothing but your CS amplifier, it gets amplified by the gain, right? So So I got the value of RMS value, and how will I calculate the SNR? See, it's a signal power divided by the noise power, right? Or in terms of mean square value, I can write it as a mean square value of a signal divided by a mean square value of a noise. Okay. Now what is this mean square value of a noise? It's nothing but the total power that we computed at the output. Clear? So I have the total noise power at the output. I also have the total signal power at the output. In order to get the signal power, the RMS value has to be squared. Clear? Okay. So again, one could cancel out some of the common terms out of this equation. So when you do so, okay. So with this, the noise analysis is done.